Now let's derive the conservation of angular momentum. For a particle, when we wrote conservation of angular momentum, we could write the material derivative with respect to time of mass times the vector cross product of the position vector and the velocity vector will equal the vector cross product of the position vector and the external force vector P, where P is the resultant of those applied forces, which in the case of our continuum will be the sum of the resultant of the body forces and surface forces. So again, generalizing for a continuum and recognizing that the resultant forces come from the surface and body forces, we can write that the material derivative with respect to time of the volume integral over R of the density by the position vector crossed with the velocity vector integrated with respect to volume is equal to the triple integral over R of the density times the position vector crossed with the body force vector integrated over the volume plus the integral over the surface of the position vector crossed with the surface traction vector T sub n, T superscript n. Writing this in components again, we would have that material derivative of the volume integral rho times eijk, the permutation symbol, times x sub I v sub k integrated with respect to v is equal to the triple integral over R of rho times the permutation symbol times xj bk integrated with respect to volume plus the surface integral of the permutation symbol times xj times tpk times np integrated with respect to the surface. Again, applying the divergence theorem to turn the surface integral into a volume integral, which will give us the divergence of the stress, and using the same reasoning as before, so that the integrand itself must be satisfied, we obtain the permutation symbol eijk times the material derivative ddt of xj times vk equals the permutation symbol eijk times the density rho times xj bk plus del xp of xj times tpk. Now, from the definition of the material derivative, we can write that the material derivative with respect to time of Vj xk will be xk times the material derivative of Vj plus Vj times the partial derivative dxj dvk del xj. So this first term is the acceleration, xj times the acceleration, ak, and the second term is vj times vk, since del xj of vk with respect to xj is vk. Similarly, we can expand the derivative del xp of xj tpk to be del xj del xp using the chain rule times tpk plus xj times del tpk del xp. Del xj del xp here is delta jp times tpk plus xj times del tpk del xp. So this term here then becomes tjk plus this term xj del tpk del xp. So now using these two expressions, we can substitute them into our expression above, take eijk outside of everything, and we get eijk times tjk plus xj times tpk del tpk del xp plus rho bk minus rho times ak, yeah, minus rho vi vk is equal to 0. Now, if we look at this term here, it's multiplied by xj, we can see that this is in fact the conservation of linear momentum. By conservation of linear momentum, this expression is 0 because these two terms equal the inertial force. Here we observe that Eijk times VI-VK are components of the cross product of V with itself. But the cross product of a vector with itself is 0 because the sine of the angle between the two vectors is 0. So therefore this term disappears, and we're left with Eijk, the permutation symbol, times Tjk is equal to 0. And now if we recognize that Eijk is equal to the negative of Eikj, which we get by switching the indices k and j, then that would suggest that the only way that this could all sum to 0 is if Tjk is equal to Tkj, in other words, if the Cauchy stress tensor is symmetric. So this is the same result we got more easily before by considering the equilibrium of the stresses. And this result only relies on the assumption that there are no distributed body or surface couples acting in the material R. And in practice, this is true for all but a few very specialized applications in unusual materials and unusual conditions that we don't have to worry about. So for all practical purposes, conservation of angular momentum requires that the Cauchy stress tensor be symmetric. There are other definitions of the stress tensor, and at least one of them is not by definition symmetric, but this underlying property of the Cauchy stress tensor and its Lagrangian equivalent, when we learn about that, are valid for all practical applications. This completes our derivations, but if you were observant, you may have noticed that I did something that wasn't completely legitimate, or at least didn't appear to be. So you'll notice here, for example, that the material time derivative of the volume integral of rho times Vi, I substituted with the volume integral of rho times the material derivative of V. That would imply that rho is constant in time, but in fact, we haven't required that. And in general, that's not the case. So in fact, this is a result that comes from conservation of mass. So I want to finish just by proving that, so that you don't think I made a mathematical mistake, or that I assumed, or that we have to assume that the density is constant. In fact, we don't. This simplification that the material time derivative of the volume integral of rho times V is equal to the volume integral of rho times the material derivative of V actually is a result we can prove making use of the Eulerian form of mass conservation. And you'll see I did the same thing down here, where here we had the material time derivative of rho times x crossed with v, so another vector in this case, and again ended up putting that material time derivative inside the integral and ignoring and not applying it to rho.